Okay, this is 5.4, the function e to the x power, and our objective will be to define and apply the natural exponential function. And that's what this e to the x is. Y equals e to the x would be the natural exponential function. And we call it natural because it occurs all the time, and I'll be talking about that momentarily. But first, let's do this. What does that e equal? E is a number, and to find that number we use calculus, all right? And then you're going to always have an approximation for e because it's an irrational number. It's a non-repeating decimal that goes on forever and ever and ever. Okay, kind of like pi, all right? And what is e? Well, they used calculus to find e, and here is what they did. They did the limit as n approaches infinity, this is calculus right here, of 1 plus 1 over n to the n power. So what is this expression getting closer and closer and closer to as n is tending towards infinity, as these n's get bigger and bigger and bigger? How cool. All right, so the first thing you study in calculus is limits, all right? And the first way you will find limits is to investigate them numerically. That means you get to use a calculator and technology. So here's what we're going to do. All right, I want you to take this expression 1 plus 1 over n to the n power and put it in your calculator as y sub 1. 1 plus 1 over x, that quantity, to the x power. And then you're going to have your calculator do a table for you. So again, go to your table setup, and you want to be able to put in any x that you want to determine this limit right here. So here's my setup. You don't really have to worry about anything. As soon as you go, the independent variable is on ask. That means then you go second table, and your table shows up, and you can put in any x value you want right here, and your calculator will give you the corresponding y values. Now, whenever you do a limit as n approaches infinity, we always use the same x's. So I'm going to zoom in here, and what I'm going to do is I'm going to make my x's multiples of 10, like 10 to the first power. So if x is 10, my calculator will tell me that y sub 1, or this expression with these n's being 10, would be 2.5937 approximately. And then just keep going higher multiples of 10. 10 to the second is 100. And the calculator tells me 2.7048. Then I go 10 to the third, or 1,000. And I get 2.7169. Now look at these numbers, 2.5, 2.7, 2.7. It looks like we might be getting closer and closer to a number. So let's go 10 to the fourth, or 10,000. And that's going to be 2.7181. And then finally, let's go 10 to the fifth power, which is what, 100,000? And what is that? 2.7183. So look at what we did. 2.7181, 2.7183. This is now accurate to 3 decimal places. So we can at this point say the limit as n approaches infinity, these n's are getting bigger and bigger and bigger, and I know in the calculator we call them x's, all right? As n increases, 1 plus 1 over n to the n power gets closer and closer and closer to 2.718 something. So I'm just going to write that. 2.718 and so on. But now we have e to 3 decimal places right here. And like you guys usually call pi 3.14, we usually call e 2.718 if we just need an approximation. Nice job. And you guys have just done your very first calculus right there. Okay, so the function e to the x is called the natural exponential function because it occurs in nature all the time. The number e, which we have said is approximately 2.718, is extremely important in advanced mathematics. We use it all the time. And again, It appears in unexpected places, including statistics and physics. For instance, the equations of each of these graphs contains an e to the x power. All right, look at this. This looks like a bell curve, a normal distribution. And what is this graph? Stats. This is the distribution of heights of 18-year-olds. All right, and again, if you wanted the equation for this bell curve right here, guess what would be in it? An e to the x. Okay, how about physics? If I have two vertical poles and I tie a rope on each end at the same height like that, the rope's going to sag a little bit. This is sagging a lot, all right? And the equation that would represent the height of this rope at any distance between the poles, okay, is also going to contain, guess what? An e to the x. So cool. This is very, very important. So let's apply this then. And this is how we're going to use e to the x in our study of exponential functions. E to the x is part of the continuous change model. So suppose that you invest P dollars at 12% compounded semi-annually. We're about to discover something. Each half year your money grows by, okay, and again, we get 12% interest, but we're compounding semi-annually. That means twice a year. So that means each half year your money grows by half of that 12%, or 6%. 6%. And at the end of the year you have, so I have my investment P times my growth factor of, and if I'm growing each half year by 6%, my rate is 0.06 and my growth factor is 1.06. And then how many times am I compounding in that year? Twice. We're compounding semi-annually to the second power. Now, guess what? If you punch out this 1.06 to the second power and do so on your calculator, you're going to get a number slightly more than that 12. Check it out. Okay, so this is going to be 1 point, and here we go, 1.1236. So you see the 0.12 is my 12%, but because we compounded twice during the year, we got a little bit more than 12%. We got 12.36%. All right, so the more often we compound, the more money we make. Let's compound quarterly now. So we're going to go P, our investment, but if we're compounding quarterly, we're compounding, what, 4 times a year? So 12% divided by 4 would be 3%, making the growth factor 1.03. And then how many times did we compound? 4 times. Now guess what? If I punch out that 1.03 to the fourth, again, I'm going to get a number slightly more than 1.1236. So check that out. 1.1255. Make sure you're doing this on your calculator too. So again, I'm making now 12.55% interest. We could do monthly, daily, etc. Okay, very cool. So we're going to do a little table, and I gave you a link to print out this table so you could just fill in the blanks. And we're going to invest only $1 and see what happens when we compound more often. So here's your table right here. Okay, and if you don't have a printer, just quickly write this out in notepaper and fill this out. And what we're doing is another table to develop a very key formula. Okay, so let's start at the top here. We've got our interest period, our percent growth each period, our growth factor during each period, and the amount of money we're going to have. So percent growth each period. Okay, well, annually means, and we're at that 12% still, so each period we're going to get 12% interest. So our growth factor, and you guys know that's going to be 1.12, but I'm going to write that in a way so I can start to develop my formula. Growth factor. Okay, and again, this little note down here, let's write 1.12 in a form that helps us discover a formula. So what we're doing here is we're taking the 1 to represent 100% of our investment plus, and we're getting 12% interest, 0.12, and we're compounding that just at the end of the year divided by 1. And that is my growth factor. That is 1.12, like we already knew. So how much money do I have at the end of the year? I'm going to go my growth factor to the number of times compounded every year. So that's just going to be 1.12 to the first power, or 1.12. Okay, now semi-annually. So every time I compound, if I'm compounding semi-annually, I'm getting half of that 12%, I'm getting 6%. Now, look at how I write my growth factor, though, so I can develop my formula. I'm going to go 1 plus 0.12, but I'm going to divide it by 2 to get that 6%. 1 plus 0.12 divided by 2. And that's going to be a growth factor of 1.06, which we already knew, but that's then going to be to the second power because we're compounding twice every year. 1.06 to the second, and when I punch this out, I get a number slightly bigger than 1.12, 1.1236. Now quarterly, so we're compounding 4 times every year. All right, so 12% divided by 4 would be 3%. So now look how I write it over here. I'm going to go 1 plus 0.12 divided by the 4. And that's going to be, what is that? 1.03 to the 4th power. And this is going to be slightly bigger than 1.1236. 1.1255. We're making more and more money. The more often we compound, the more money we make monthly. So, well, that's going to give me 1% every time I compound. So I'm going to go 1 plus 0.12 divided by 12. All right, and that is what? 1.01 to the 12th power. And if I punch this one out, guess what? Slightly more than 1.1255. 1.1268. Right on. Daily. Now, how am I going to write this? Because daily, I'm compounding 365 times a year. So I'm going to write this as 12 divided by 365%. That's going to be my percent growth each period. All right. And now over here, look what I do. 1 plus the 0.12 divided by the 365. All right. Now, if I punch that out, that's going to get all ugly. So I'm going to do my growth factor just like this and do that to the 365th power. There you have it. And we're starting to develop something here. Look at this. My growth factor, 1 plus 12% divided by the number of times I compound in a year to the number of times I compound in a year power. And if you punch this out, you're going to be slightly more than 1.1268. 1.1275. Okay. Now, I want to tell you something very important that's going to make your life much easier. Daily is equivalent to continuous growth. So if they say something compounds daily, you're going to use another formula for continuous growth that I'm going to give you right at the end of this lesson here. Okay? And now we take what we've done and see if we can come up with our formula for K times per year. So wouldn't this be 12 divided by K percent for my percent growth each period? Yes, it would. And now I'm going to go over here, 1 plus 0.12 divided by K. And then this becomes 1 plus 0.12 divided by K to the K power. And there it is. There is my expression for anything that's compound interest. So I have my interest rate, divided by the number of times I compound in a year to the number of times I compound in a year power. All right, and this is a a compound growth function. Again, we'll talk more and more about that. Very cool. All right, so, and look at those numbers again. Our 1.12, our 1.1236, and so on. Those numbers are right up here in red. And again, it looks like we are approaching a fixed value. Do you agree? We're getting closer and closer and closer to that, like we're at 1.1275 right now. So let's find it. Now, we're not going to do this numerically. We could. In fact, we did already. And doesn't that look very similar to what we did with E? So we didn't do this one exactly. But we're going to use E here and manipulate this expression to put it in the form of our definition of E using calculus. And what was E again? It was the limit as n approaches infinity of the quantity 1 plus 1 over n to the n power. Now this is close to that, 1 plus 0.12 over k to the k power. So see that 0.12? I'd like to write this all in terms of E, so I want that 0.12 to be a 1. So that's just simple algebra. Okay, I need a 1 in my numerator right here, so I'm just going to put it there. Now, I can't just run around putting things where I want them because it fits, all right, the formula I'm looking for. So I need to manipulate so this is a true statement. So I took this fraction, 0.12 over k, and I want to write it as 1 over the reciprocal of that fraction. So this would be 1 over k divided by 0.12. Look at that. Okay, so I'm getting closer. 1 plus 1 over n, and now I'm saying my n is that k over 0.12, but then I need that n right there too. So I need this k, this power, to also be divided by 0.12. So could I use laws of exponents to make that happen? Let's see. Well, what if I said, let's take that k and divide it by 0.12. Now, again, I can't just do that because it fits my formula. I now have to undo that. So if I divided that k by 0.12 within the brackets here, I'm using my power of a power, and I'm going to then take that entire expression to the 0.12 power. And again, all I'm using here is my power of a power right here. B to the x to the y is b to the xy. So if I do that, I haven't changed anything, but look at this bracket. 1 plus 1 over k divided by 0.12 to the k divided by 0.12. So I'm saying the n's I see in my definition of E are nothing more than k over 0.12. All right? And again, if k is approaching infinity, like n is approaching infinity up here, then this expression and this expression are going to both converge to the same thing, that E, which is approximately 2.718. So guess what? That equals 1 plus, and again, I'm going to let this k over 0.12 equal n, and that k over 0.12 is also n. So I've got my E, because n is approaching infinity, to the 0.12 power. And what did we actually do here? What we're doing is we're developing, I have my base E, or 2.718 approximately, to the 0.12 power. Wasn't that my rate, my growth rate right there? So that is approximately, now let's punch this out, and guess what? You see that 1.1275? 1.1275. Okay, approximately. All right, so that's why I said earlier that daily, if I compound daily, that's going to be the same result as if I compound continuously, meaning these ends are getting bigger and bigger and bigger. We're still going to be approaching 1.1275. So R is, now we went from 12% interest if we compound once per year to approximately 12.75% annual yield. So we're getting closer to 13% because we are compounding daily or continuously. So that e to the 0.12 is the same thing as e to the r power right there. And we're going to use this for our continuous change model. Okay, so this is it right here. Continuous change. So this is another exponential growth model we're going to add to our tool belt. P of t equals our initial value, or if we're investing money, our initial investment, times e to the r, and that's the e to the r we just developed on the previous slide right there, to the t, or r times t, and t is the number of time units that we're doing this. You know, it might be years, days, minutes, whatever. All right, and this is my favorite continuous change model or exponential growth model, because the exponential formula, when compounding is continuous or occurs all of the time. And I also use this if they tell me something is going to compound daily. So we better practice this before I turn you loose. All right, so in my backyard, and it's remote learning right now, and I'm sitting in my bedroom at my desk, I'm looking out at my backyard, and my backyard is surrounded by laurel trees. They're bushes, trees. To me, they're trees because they're huge. All right. And when I first moved to this house, you know, almost 20 years ago, every spring I would cut them down to the fence level, right at 6 feet. All right. So I decided I'm going to use this situation to show you guys how we use P of t equals P sub 0 e to the RT. So I cut them down to 6 feet. That's my initial height of those trees. Now, laurel bushes grow very fast. And I approximated, and I think this is a pretty darn good approximation actually, and I'm approximating that my laurel bushes grow by about 38% every year. And what do plants do? They grow continuously, right? So if I did not cut those trees down to 6 feet every year, how high would those laurel bushes get in, let's say, 3 years? Well, they're growing continuously, so I'm going to use this model right here. So I'm going to go P of 3 equals, and I cut them down to 6 feet, and then I'm going to go my e to the r, and we've got to make sure this r we put in as a decimal. Don't go e to the 38, or you're going to see some really big bushes out in my backyard. So it's actually e to the 0.38. Always write your percentage as a decimal when you're using the continuous change model. And then times t, the number of years, 3 years. And I punch that out, and guess what? If I don't cut my trees down for 3 years, those 6-foot laurel bushes will be 18.76 feet tall. And I'm looking in my backyard right now, and I'd say those trees are exactly, well, very approximately about 19, 20 feet tall. That's a really good model right there. And guess what? I haven't cut them down in 3 years. All right, that's what I'm looking at right now. And it's cool because that makes my backyard totally private. All right, we have a pool, we have a hot tub, you know, and my backyard is my castle. I can do anything I want in my backyard because nobody can see into my backyard because of those laurel bushes. All right, now I'm worried they're going to get too tall and come down in some bad storms eventually, but for now, I'm enjoying my privacy. With that, I want you guys to do 5.4, 1 through 13, 15, and 17. You guys have a great day. Hope you enjoyed this lesson.